So hi folks, I'm Sam. I am founding engineer at Boundary ML. We, among other things, build a programming language for building LLM-powered applications. And so in the process of building this thing, we have also exposed interop for everyone, because all of our users not only write their code in our language, but also Python, TypeScript, Ruby, whatever, what have you. And so what I'm here to talk about today is all the things you want to think about when you're doing this cross-language stuff. Show of hands, how many people have worked in cross-language code bases before? Like anything where you have, cool, okay, so you've all dealt with the problem of having types in two languages sucks. So just a few notes on talk. I've got 25 minutes for this. I don't need to go longer. Cool. So please ask questions. I'm happy for people to interrupt me. I will probably sprint for some stuff. There are still one or two slides in this talk from where I gave it separately that are not Python relevant, but the concerns are still the same. So first thing, you probably shouldn't do this. As everyone knows, right? Like if you've dealt with things in multiple programming languages, there's overhead that comes with working in multiple languages. There is a significant ongoing tax that you will pay for dealing with problems in one place and then dealing with the same problems in a second place all over again. But sometimes there is a good reason, and I'll talk about some of those reasons. And if you do have those good reasons, then you need to make some decisions that you will find out the hard way and will be very frustrating if you don't think about them ahead of time as you go forth. First problem. Okay, right. So structure, I'm going to sprint through like the reasons you shouldn't do this. The first reason is that you will run into a lot of scary bugs. This is a compiler error message that you will get faced with probably within the first 30, possibly within the first 30 minutes of doing this. And that's just because error messages are hard. So not much you can do about it. The fix isn't that hard. Your release process gets way more complicated. Like it's really nice that when you have a GitHub workflow, just see like box, 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 and we have a lot of boxes on here, and debugging them gets very painful, especially because when we're building for Python, right? We now can't just ship Python code, but we have to ship architecture-specific versions of our Python language. So we have to ship a Mac ARM64 version, we have to ship a Mac Intel version, we have to ship a Linux Intel version, Linux ARM, Windows. I don't think we ship Windows ARM. I think we only ship Windows Intel right now, but I'm not 100% sure on that. I see 7. I don't know how to do multiplication right now, so I'm going to ignore that. Oh, and also, remember, like everyone's dealt with the pain of like fixing your GitHub actions every single time it breaks. This just gets worse. The problem multiplies because you have many more jobs, many things that you have to do. I'm going to skip Ruby because Ruby's not important here. In terms of why, one of our goals, right, as BAML is that we want people to be able to write BAML. So that's the screenshot at the top. And then down here, you'll notice, right, the resume object has 4 fields on it. And if you're in Python, we have actually made it so that as you're dealing with Python objects from your BAML client, you can literally get auto-completion of your BAML code in Python, right? So if I'm typing resume, I can just type out resume dot, and then my IDE will just auto-suggest email, experience, name, skills. And we do this across multiple languages. To be able to do this effectively, like without introducing bugs on every single language implementation, you kind of want to go into a common layer, do all of that complicated logic in one place, and just do wrapper shims for everyone who talks to you. So in our case, our polyglot product library requirements were the things that really drove us to do this. Your other option, if you don't do this in Rust, is to do this either in C or C++. We have Boundary have all written C and C++. Half of us now. None of us want to do that again. Also, Rust lets us move fast and not break things. Our 2 co-founders wrote their first Rust code in October 23. I joined in February 24 and started writing Rust effectively basically 3 months before that. We're now a team of 6, and we still don't do code review by default. And I don't know, we're up to what? Past 100 7,000 lines of Rust apparently. So that's a lot of code to not be doing code review. And because we have the guarantees that the Rust compiler gives us, and the things that we can do in how we write our code, we have a lot more structural guarantees that exist within our code base, that if we were doing this with Python, we would have to spend a lot more time writing tests and talking to each other, and frankly, doing code review. Because there's no other way to encode those invariants in the code base. This point doesn't quite make as much sense unless you've seen some Rust. And I can, if people want to ask more about this, I can talk about that a little as I go into demo. So demo time. So let's see some code. All of this, right, is like it's very fun, it's very fancy sounding. It's also scary because like all you've heard about Rust is like, oh, it's this horribly complex thing. Which, to be fair, I didn't help with that because the first thing I showed you was a terrible error message. But at some level, right, like it's still code. There are a lot of resources for making this comprehensible. There are people who know how to do this, and you can ask people like me questions about how this works. So what I have here, right, this is just some Python code. I'll make this a bit bigger. Is this better? Cool. Cool. Okay, I will make everything else a little bit bigger as well. So this is just Python code. There's an import statement for my Rust crate, and then I'm just going to do hello world in my Rust code. And the Rust code itself is not, there is a lot more stuff here. I'm going to not mouse over that so you can see it. And it's just println, right? That's not that scary. The other stuff maybe looks a little scary, but println isn't. And then if I'm going to run it, let's make this a bit bigger too. So the whole stuff around compiling, and then I can just run. Oh, and look, I'm getting hello world. What I can also do is I can say hello world from Rust. And if I flip back, Python code is still the same. Let's actually keep them open and go like this. Python code is still the same. I will have to rebuild and hello world from Rust. You can take this really, really far. So I can go and say, actually, I'm just going to comment this all. And I'll say my Rust crate. No, I do not. Bad cursor. Stop suggesting magic things that I don't want to actually do. Start server via Tokyo. And I'm just going to say I'm going to run a server on localhost, port 3001. We'll build, we'll kick off the server. I have an HTTP server now, listening on localhost 301. Now I can curl it. And voila, I have a server that goes pong pong pong. Questions? Okay.
What's Tokyo? Like the city.
I will, that is not a thing I should have had in that example code. That is a thing that opens up a lot of questions about why Rust is complicated, so I'm going to hold that question for later. That is a good question. Okay, this code is a little small, I do apologize for that. But so, in terms of like questions that you now have to think about if you're going to go and do this, you need to ask yourself what kind of API you're going to give to your users. If you put a lot of your logic in your Rust objects, a thing that you're going to have to do is start implementing everything that Python does for you out of the box. So, for example, you have to now hand roll your constructors, right? Like normally you can just like override init, but you do not get these out of the box if you just start defining your Rust objects in Rust. You don't get a string representation out of the box. You don't get a repr method out of the box. You don't get a hash method. You don't get a get state or set state, which if you're doing anything that involves pickling, you will need. So to concretely show you what I mean by this, I'm not going to keep main.py and yes, I do have a my Rust object. So So what I'm going to do here is, where did I call it? I called it my Rust object. So in Rust, I have this code that says, okay, here's a static method, returns an instance of self. Oh god, mouse over. Which is just saying, okay, this is going to return a my Rust object, and then there's this annotation that's basically the Python version of like the static method decorator. So if I do this, my static method, hello world, do not do that. And I do have this. So what I have right now is I am saying in the string representation of this object that this is going to throw a runtime error. So if I now go and run this code, I'm going to control C out, I get a runtime error when I run this, when I run like this existing code, right? If I comment this out, and then I rerun this is going to get, this just gives me gibberish. Built-in's my Rust object at random memory address. If I'm debugging a library that is written in Rust, and I just try to print an object that is handed out of this like my Rust crate, and I get this, my first reaction as like a person writing Python is going to be like, what the fuck? Why? This is useless. I don't know what is going on inside of here. So if I'm doing this, right, like I expect this representation to hand me back some kind of information around like, oh, what is inside my Rust object? So if I do this instead, where I say like, okay, string can return, like the string refer object can return like, okay, and it hands back a string object. Now, Python code is still the same, I'm just printing it. And now I get, oh, what's inside that Python object, or that Rust object, is a thing that says, created by a static method, hello world. But the key here, right, is that I had to go and do this by hand. If I just define a Python object myself, I don't really need to do this in a lot of cases. And that goes for like all of the other magic Python methods that get attached to a whole bunch of objects just out of the box. Things get significantly more complicated if you want to deal with async await code. Show of hands, how many people have written async code in Python? Cool, okay, so a bunch of folks. You've definitely run into the fact about being confused at some layer of like, okay, what is the async IO module? Why am I going to do things as like a coroutine versus like threads versus like, do I need to think about the GIL or other stuff? And that is all perfectly true. Like just as a general rule of thumb, like writing async code is annoying. It raises a lot of questions where you have to think about not only how your code is working, but how it interacts with the underlying like asynchronous abstractions that you are working with in Python. And then, if you're crossing a language boundary, you now have to ask questions about how it works across the Python Rust boundary. So the easy answer to how do I deal with like Rust async abstractions in Python is that you don't. And so that's what this comes back to the question I got earlier about what is Tokyo. So let's delete this. My Rust crate. Nope. Start server via Tokyo. And so one of the things I've done here, right, is I have installed a Control-C handler. If I comment this out, and I now run this code, I am spamming Control-C now.
Soft lock?
Say again?
Soft lock?
I am effectively, yeah, like I can't regain control over this because under the hood, Python has like, itself has code that says like, okay, if you press Control-C, I'm just gonna shoot your Python program in the head and tell everything to shut down cleanly. If you're doing this across the boundary, in the most naive way, it is not going to work out of the box, and voila, you now have another problem that you need to go and fix. So what I'm doing here specifically is the most naive possible like implementation of, I'm gonna just press enter a whole bunch of times so that we can only focus on this code. So Tokyo is basically the Rust version of the async IO module. For assorted reasons, this is a library in Rust, just like it is in Python, and is not really a core part of the Rust language itself. And so what I'm doing here is I'm saying, okay, I'm going to start an async runtime. So essentially, I'm going to start like a magic like VM, a magic just black box that I'm going to start mousing over stuff. I'm going to start a magic black box and just say, okay, I'm going to hand you an async thing, hand you a coroutine, hand you a future, and you're just going to go do it. And I'm going to block until that thing finishes. But, right, because it's blocking, and what I am doing in my Python code now is I'm just running this, because it's blocking on the Tokyo runtime, running this async thing, this thing doesn't know about the Python signal handlers that exist that normally listen to Control-C. And now all of a sudden, I have to reintroduce this. How am I doing on time? 15 left, I'm guessing? 10? 6. 6, okay. Overestimated. So that's the next slide. So there's a whole bunch of things you have to do, right? And like across different languages, this also changes. Fortunately, this is a thing that a lot of other people have dealt with because Python is a popular language, Rust is a popular language. Many people like writing code in async so that they don't have to do stupid lock-on things. There are people who have solved this problem of like, okay, I want my Control-C to just work, and I don't want to have to do like weird shenanigans, and I want to be able to actually write async code in places. I'm going to skip over this slide because this is like low-level details that aren't super important. But to hop back to show you what that code actually looks like, this is where I can say like, okay, I can actually do async IO, and now of course I need to now refactor all of my Python code because colors are stupid. I really hope I actually remember how to write async code in Python because it's been a hot few seconds since I've done it. I need to find this thing. And now this time, right, I'm going for async IO. What's happening on the Rust side here is I am saying that, okay, I have a Rust method, start server via async IO. It's getting added to the module. And this Rust code is going through this like community provided because, again, many people use Python, many people use Rust, many people use Tokyo, many people want to use async. They want to do this thing the same way. So I have this thing that converts a Rust future, which is essentially a Python coroutine, into a Python coroutine, which are abstractly the same exact things, right? They're just things that say, okay, at some point in the future, I want this to finish. But the actual like physical like layout in like computer bytes are different. So there needs to be a bridge to handle that behavior, and also to like do things like transfer like signal handling across the boundary. And now if I do this, I can just do curl again, and voila, it works. But this time my Python code looks different, and I actually have asyncs, and like now I can do a whole bunch of stuff with like saying like, okay, I'm going to create this coroutine, I'll await it somewhere else, and now I can do other async stuff in the background because like, oh, the Python like runtime and async IO is actually letting me do stuff around async scheduling. In order of difficulty, this is another thing you kind of want to think about, and like, again, like remember this trade-off, right? Like async is harder than synchronous code. If you're just doing synchronous code, it's fine. If you pass in objects, it gets a little more complicated. As you start adding async stuff, there's a bunch of different ways it can work, right? Maybe the Rust code just hands back a feature that you need to await on. If you want to do stuff with callbacks, it starts getting a little more complicated. If you want to hand an async callback in Python back into Rust, that gets really heinous. So this is another level of like design thinking that you'll want to keep in mind. And keep in mind that this isn't only stuff that you're going to have to deal with the implementation side, but your users will have to think about what problems might happen if they have to debug this. And that gets really painful. There's a long additional laundry list of issues. Cross-compiling still sucks in 2025. The ecosystems are smaller, right? There's a lot of people who write Python, there's a lot of people who write Rust. People who write Python and Rust at the intersection of those communities, and that is a bit smaller. Skip the PyTrip stuff. Python has its own TLS semantics. I have not really had to deal with this yet, but I know we have to at some point when we start getting questions around why people, because we do not respect the TLS certificates, that like if you do stuff with requests and override that certs there, we are not going to respect those. We have a separate TLS loading path, and that's another problem you'll have to deal with. Language versions, a lot of people still use Python 3.8, even though it's end of life. Coordinating package versions, that's another one. We solved this problem by just like saying that like we're going to move them in lockstep. If you want to desynchronize them and say like I want to be able to release my Rust crate independently of my Python wheel, you're going to have fun. And now you have to explain to people why they're two different versions, because maybe you want to release them independently, but then you get confused. If you want to take a look at what this actually looks like, do take a look at our repo. Give us a star if you want. Yeah, that is us. Thank you all for listening.